All right, we'll go from current slide. I think I made the announcement before. Alabama A&M does have the North Scholarship Program, but they don't do the summer programs like UAB and Alabama did. They just do pay your tuition the last 2 years, so that's pretty good, but they're not trying to coach you in. They just, well, I guess they are trying to coach you in, but they, no summer programs to whet your appetite, we'll put it that way. All right, any questions on anything we've done so far? I just realized I have 2 marks on the same page. I have a feeling it's the second mark here. I think we were going to go over the procedures for solving the linear equations. Is that right? Because I think we did the integrating factor. Page 56. Oh, and by the way, I forgot to ask my last class this. Had I given y'all the code for the WebAssign?
No.
Not that you need it, because I'm not going to make any assignments on it, but it does have tutorial help and more problems to practice on. So if you need it, here is the code. Yeah, that might help. But I didn't think you needed to see anything today. You could just listen to me and absorb it all. Okay.
Radio lectures.
Yeah. Okay. Here is the code. Lawson.al. Let me get my pen set up. That's a little L there. My pen drags a little bit. So don't put a capital L. Lawson.al space 0033 space 3638. So I don't know if it's required to access ebooks now, but you've got your own book, so you may not care about that. But again, they do have tutorial help and other things too. I haven't looked at it to see what it's like, because I don't make assignments on it, but it's supposed to be a pretty decent package. What I don't like about all of those computerized packages, and maybe especially, not especially all of them, they're computer driven, and they're not AI by any means. They're just someone fed in, this is an answer. So if you had x over 2 and it was supposed to be 1/2 x, they would say wrong, wrong answer, because it's not the one that whoever programmed it told it to recognize as the correct answer. And they don't have multiple correct answers as far as I know. Okay. So anyway, that's the code if you need it. So, how to solve a linear first order equation. First and foremost, get it in standard form. Now, standard form for different types of equations or different ways. The standard form for a linear equation is the one given on page 55, previous page. We talked about this last time. So first, standard form. Okay? The standard form looks like this. dy dx plus some p of x, y. I was going to put f of x, but they're not doing f of x now. They're using y. Is equal to some, this is where the f of x goes. Okay. All right. That's standard form. Your derivative term here, your function term there, with possibly a coefficient here. You can't have a coefficient of the derivative. If you do, divide it through, and get rid of it, make that a 1. And then that changes your function there to being whatever it would become. That's your function of x. And then on the right-hand side, only functions of x. Only. Okay? You can't have any y dependence over there. And remember, to be linear, the first derivative is only at the first power, and the function can only be at the first power. You can't have any y times dy, and you can't have any cross terms. That's your standard form. Get it in that form first. In doing so, you identify your p of x, and that's what we build on. Okay? From the standard form, identify the p of x. There it is. Okay? Then find the integrating factor. Okay? The integrating factor is going to be the integral of p of x dx. So once you find that, well, actually, okay. First, find the integral of p of x dx. Okay? First do that. Now, when you do that, that looks like an indefinite integral. It is. But don't put a plus c with it. We'll wait and hold off the plus c's till the end. Just do integral of px dx. Then, that will enable you to identify the integrating factor. Okay? And that will be e to the that. E to the integral of p of x dx. Okay? Now again, p of x is just a function of x. The integral of p of x dx is just a function of x. That becomes your argument for your e function. Okay? Now, you don't need a plus c with that integral at all. Okay, number 3. Multiply both sides of the equation, the standard form, by the integrating factor. Okay? So you'll multiply everything on both sides by that integrating factor. So that would be e to the integral of p of x dx times dy dx plus integral of e, I'm sorry, did it backwards, e to the integral of p of x dx times p of x times y is equal to e to the integral p of x dx times f of x. Okay. Now, here's where the magic happens. Okay? This always is a perfect derivative of a product. Okay? The product would be y make sure I say this right. Yeah, y times p of x, I think, or is it e to the x? No, e to the, yeah. So this is a perfect derivative of, this is a product rule here, and this will be a perfect derivative of e to the integral p of x dx times y. Okay. Yuck. Okay. Yuck. Now, okay, let's make sure that's true. Derivative of this product rule would be this thing times the derivative of that. Yeah, there it is. Plus this, there it is, times the derivative of this. Well, derivative of e to the this would be e to the this times derivative of this, which would be derivative of an integral is p of x. And there it is. So this automatically, that's what the integrating factor does, it automatically gives you a d by dx of a function here, okay? And this contains y and y alone, no derivatives anymore. And then you have some function over there. Well, that's just some function of x multiplied by another function of x. So what we do This is e to the integral p of x dx f of x. Just multiply those two together. Whatever those two functions are, multiply them together. Okay? And then, sort of like multiply by dx. And now you integrate. And there you have it. Yes, this, by the way, the integral of a derivative, of a perfect derivative, is just this. So now you have a product here. Okay? That's it. You have e to the integral p of x dx times y. The integral of a derivative is just what's inside. And then this is just some integral. Evaluate it. Okay? And once you get it evaluated, then divide it by e to the integral of p of x dx. Okay? So whatever this is, divide it by that integral e to the integral p of x dx. Okay. Now, let me say one thing. Integrate that p of x dx, this just gives you a function of x, right? You don't have to carry around that verbiage here. It's just some function. And then raise e to that function. Okay? And that gives you a function. Okay? And then from then on, that's what you're dealing with. You're having to write all this, but guess what? It's just a function. And that's what you don't divide by and everything else. Well, you actually do the problems. They're far easier than these steps. Okay? And I included 4 there. Okay. So let's do example 1. So much easier than all that mess. Okay? So here is dy dx minus 3y is equal to 0. dy dx minus 3y is equal to 0. Now, before we do anything else, you know this could be solved by separation of variables. Okay? That's the easiest way to go. That's how you would normally go. There's no reason to do the linear form here, except just to see if we get the same answer. Because we know how to do this on the other. So what you want to do? You want to do it separation of variable first and then come and do the integration? I mean the linear? Or you want to do the linear and then do the separation of variable? I don't care. We're going to do it both.
Ideally, I'd like to do the integration first, I think.
The linear or the separation? They both are integration, but you know.
Yeah, let's do linear first.
Linear first, okay. First, get it in standard form. Is it?
Appears to be.
Yes, it is. Okay. Now, and this is also homogeneous, so that's going to make it really easy to do the right-hand side. I think I can do that one. Okay. What's your p of x? That's the next thing. Once it's in standard form, then you identify your p of x. What's your p of x? It's the coefficient of your y.
Oh, which is minus 3. Right?
Minus 3. Perfect. What do you do with that p of x? We integrate it.
Oh, okay.
Dx. And since it's minus 3, I'm going to put the integral over here of dx. Okay? Well, this integral is then what? Integral of minus 3 dx.
It should be minus 3 x.
That's it. Don't worry about a plus c.
Okay.
Okay, just minus 3x.
Okay, so you have it going to do like, yeah.
Okay? Now, what do you do with that? You raise e to that power. There's your integrating factor.
Okay.
That's it. Okay. Now, what do you do with that integrating factor? Multiply it by both sides of the equation. So this will be e to the minus 3x dy dx minus 3 e to the minus 3x y is equal to 0. Okay, right-hand side is pretty easy. Okay.
So the y becomes equal essentially to the e of x, or the derivative of x.
What's that?
Is that the y becomes essentially equal to the, actually no, the y is still there.
Yeah, it is still in there. Okay. Now, I rearranged the -3 and the y, but they're all still in there. Okay. Now, this supposedly is a perfect derivative. Okay. This should be a d by dx of e to the -3x times y. And that's equal to 0. Pretty easy. Let's make sure that's the case, though. Okay? Derivative of this would be first times derivative of the second. There it is. Right there. Plus the second, y, there it is, times derivative of the first. Derivative of the first is e to the -3x times the -3. There it is. Okay? Now, all you have to do is now write this in differential form and integrate it. Okay? I guess I probably should leave that on the inside, because this will be e to the -3x times y. Integral of a perfect derivative is that interior, is equal to, if I'd have put it on the inside, this will be some constant. Just some constant. Okay?
Is that homogeneous, or
What's that?
is it equal to a constant because it's homogeneous, or is it?
Well, it's because the antiderivative of 0 is a constant.
Yeah, because it's going to be, okay, yeah.
Yeah.
So it is because it's homogeneous.
Yeah, I mean, now, what we do now to solve for y is multiply both sides by e to the x, 3x. So that e to the 3x. There's our solution.
I see how that all, I see how that all comes together now.
Okay?
I was kind of lost in the intermediate steps there because I didn't realize where it was going.
Right. And they won't all be that simple, but I mean, most of the time they work out pretty straightforward.
That's a good demonstration of why things end up where they do.
All right. Let's do it the other way fairly quickly, I hope. This will be dy dx is equal to 3y, right? Just add that to both sides. Okay. Then let's get the y's on one side and the x's on the other. So dy over 3y is equal to dx, right? Well, I'm going to rewrite that slightly to be 1/3 dy over y is equal to dx, right?
Is that not taking out a standard form as a coefficient on the y?
What's that?
Is that not taking it out of standard form though, since there's a derivative on the dy? I know derivative. There's a coefficient on the. You weren't supposed to have any coefficients for the standard form.
Oh wait. Okay. What we're doing is we can do it that way too.
No,
We could have just divided by y and left the 3 over here. That'll give us the same thing.
Oh, okay.
Okay.
So just
Same
rewrite the
thing.
Okay.
Okay.
All right.
You're right. That's probably a little simpler rather than introducing that. So all you do is integrate. And what's the antiderivative of dy over y?
Just y.
No, dy over y.
dy over y is oh gosh, it's like a fundamental theorem and I can't remember.
No?
It's is it natural log of y?
Natural log of y. And what's the antiderivative of 3 dx?
3x.
3x. You got it. And then, I hope it's pretty obvious what you do next. Exponentiate both sides.
Try to get rid of the natural
Oh, wait. And you had a plus c somewhere here.
Yes.
On one side or another.
Right.
And when you exponentiate,
So e cancels natural log.
yeah, so that's y is equal to
E to the 3x.
e to the 3x I'm going, yeah, I'm going to put it up here with this right now, okay? And then I'm going to say, well, this is y is equal to e to the 3x times e to the c, right? Yeah, because, yeah. And then, well, just make that a new variable and put out in front, y is equal to, what they usually do is go back and change this and make this a C1 or something like this. Now make that a CE to the 3x. And that's exactly what we got here.
Huh. Yeah. I forgot about that whole exponent.
And Daniel's here. All right. Okay. We just did example 1, bottom of page 56. We had talked about how to solve the linear first order equation. I'll go back through those steps as we do the next one. Okay? And by the way, this is good for any real number x. You can do minus infinity less than x less than infinity. Because usually you do give the interval over which it's valid, but because either x is valid everywhere, this is valid everywhere. The only thing that might make you pause here is we did have an absolute value of y here, okay? Because when you do the natural integral of dy over y, you have to put that. But guess what? E to the 3x is always positive.
Right.
Always, okay? And then adding a c to it, still always positive. So you can lose that. Yeah, the x's, x can be negative or positive, and y is always positive. So that answer, unless c happens to be negative, we'll just don't allow c to be negative, okay?
So it has to be absolute value of c? Or
no, just make it c, just say c can't be 0.
Right? C greater than
Greater or equal to 0. We really don't want to equal to 0. That loses all meaning. It's a trivial solution, which of course is going to work because it's a homogeneous or homogeneous equation. But it could be 0, and that works. But most of the time we just assume it not, because if you're looking for 0, that's not much of a solution. Okay. All right. Let's go to example 2. You can get everything that led up with that, when you listen to this exciting video afterwards. Okay. It's not that funny. Okay. Now, here's the next one. dy dx minus 3y, have we seen this before, is equal to 6.
Oh, so you're just saying equal to a different number.
Yeah. Now that one little constant there rather than a 0, unfortunately, let's see. Yeah, you could still separate variables, okay? Because then you'd be dy dx is equal to 3y plus 6, and then you can divide by that, or leave the 3 over there again, and you could do it. And we may come back and do it just to verify our answers there. But let's see what happens with this one. All right, now, this is a linear, first order linear differential equation, okay? To solve this using the method we call solving a linear equation, we get it in standard form. What is its standard form? The first term is just the derivative. No constants, no functions, nothing in front. If you have anything in front, divide it out, okay? So, this already has nothing in front except 1, so that's fine. Then, you want only some function here of x. Well, this doesn't even have any x's in it, but it's a constant function. So that's fine. And over here, we only want functions of x. And that's fine. This happens also to be a constant. The y, of course, has to be just the first thing, but you can't have any x's here, you can't have any y's here. You can't have any y's here. If you have x's here, divide them out. Okay. You can have x's here, that's be fine. And there. Okay. So this is in standard form. dy dx equals some function. We call it p of x times y plus p of x times y is equal to some f of x. These are pretty easy because both of those functions are constant functions. All right. Write it in standard form. Step number 1. Done. It already gave it to us that way. Step number 2, identify your P of x. There it is. P of x is equal to minus 3. Remember, the standard form is plus P of x. This is a minus 3. Normally I wouldn't go over this again because we just did it, but because Dan just came in, I want to do it fully. Next, integrate that P of x. Okay? dx. Okay? Well then, the integral of P of x dx is equal to what? Minus 3x. Yeah. Don't do a constant with it. Yeah. Don't do a constant with it. Just leave it like that. Okay, now that we got the integral of that, the next thing we do is raise that as a power of e. So we'll do this on both sides. Okay, now this is what we call our integrating factor. All right, you take that and multiply it by everything on both sides of the equation. So you have e to the minus 3x dy dx minus 3 y e to the minus 3y. Okay, I hadn't written it like that before, but that's what it is equal to e to the minus 3. That's an x there, it's not a y. I knew that didn't sound right. Okay. Okay, good. Okay. E to the minus 3x times 6. Okay? So you multiply, you wrote it in standard form, identify the coefficient function for your y, that's your P of x, integrate that P of x, that becomes the argument of an exponential function. We did it. Then you take that exponential function that you have from that, multiply it by everything on both sides, it's called the integrating factor, and now we integrate both sides. Okay? We'll do that in a minute. Here's what I want to do first. I want to notice here, because by doing this, supposedly you guarantee that this is going to be the derivative of a product. Okay? You want to, that's what you want it to be, and we want this to be d by dx of some product function. And what is the product function? It's your integrating factor, e to the minus 3x times y. Okay? All right. Let's see if that's the case. If it's not the case, you can't do it. But it better be the case, because that's where we did it. Well, what's the derivative of the product? The product rule, right? So it's e to the minus 3x times dy dx. That part's fine. Plus, well, there's a minus, so that may be a problem. The second, y, times the derivative of the first. The derivative of e to the minus 3x is e to the minus 3x times chain rule, good old chain rule, minus 3. And there it is. Okay? So sure enough, that is a perfect derivative of a product. Okay? Well, what we do now, much to mathematicians' chagrin, we multiply both sides by dx. We write it in differential form. That's the better way to say it. Okay? So now we have a perfect derivative here. So we integrate that, and we integrate that. Okay? Integrate both sides. And the integral of a perfect derivative is just the argument. This is e to the minus 3x times y. And over here we have a 6. Now we have to do the integral of e to the minus 3x dx. What in the world would that be? Antiderivative of that. Anybody? E to the minus 3x. That's why I love doing this with e's. It's the same, except we got a little chain rule issue here.
It's over 3, right?
over a negative 3. Yeah. Okay? Remember, since you do an antiderivative, you divide by it. If you're doing a derivative, you multiply by it.
Doesn't that become a negative 6?
Okay. So this will be a negative 2e to the minus 3x, right?
Yeah.
All right. Now, guess what? We got an e to the minus 3x on both sides. So let's just multiply both sides by e to the 3x. And they go to 1. So what we have here is y is equal to, oh, I needed to have my plus c in there. Minus 2 plus c. Can it be that simple? Or c plus t, c minus 2?
The book showed us y equal to minus 2 plus c e to the 3x.
Okay, I must have left something off here. Oh, wait a minute. I do this. Sorry. I got carried away here. I did it one step too late. When you integrate this, you get 2 plus c. Minus 2 plus c. Okay. Or I'll prefer it c minus 2. Okay. Now what I'm going to do, that is at this step, and I'm going to multiply. Okay, sorry. Let me. I did too much here. Okay. Let me get rid of this and rid of this. All right. Once you integrate, you have to put the plus c in there. Okay. So let me also erase this. Sorry about that. Yuck! My eraser's not picking up. There we go. Okay. All right. Okay. All right. I'll do my plus c there then. Okay. Now I multiply both sides of the equation by e to the 3x. Okay. And that'll wipe out this. It'll wipe out this one, leaving us a minus 2, but it doesn't wipe out this because your constant is still there, e to the 3x. Yuck. Okay, so now we have y is equal to, and I prefer writing it the other way, c e to the 3x plus 2. Okay. You're right. I swap sides and then kept the sign the same. There we go. Okay. I'll fumble my way through it somehow here. Okay. Now. That's the key here. You have to do the integrating constant once you do this integral, and that usually gets involved with that e to the 3x, or whatever your integrating factor, because you've got to multiply that through. Now, did you want to just, for fun and practice, go back and see if this was separable? Good. Okay, that would be dy dx, going back to the original equation here, is equal to 6, well, let's do it this way. 3y plus 6, right?
Yeah. Negative 3y.
No, we added it to both sides.
Negative 3y.
See, yeah.
You're right.
Yeah,
all right.
Add it to both sides. Okay. Now, I also want to do this, because I don't want to carry around the 3. 3 times y plus 2. Is that all right? I just factored out a 3. Okay. Now, can I erase my answer here? Y'all remember what it is, right? You have it written down, right? I can write it down here if you want me to. I think you probably do. Y is equal to, I just had it. Wasn't it 6 plus c e to the 3x? Was that it? Was it 6 or was it 2?
It was CE.
It was negative 2. Yeah, I'm sorry. I'm trying to do it from memory. Negative 2. Okay. Or I prefer to write it the other way, but that's fine. Okay. All right, so what we're going to do here is separate the variables. That means multiplying both sides by dx and dividing both sides by y plus 2. Okay, so I'm going to write that a little bit neater. dy over y plus 2 is equal to, these go out, 3dx. Separated the variables, right? Now we integrate both sides, right? Okay. And this gives us the natural log of y plus 2 is equal to, goodness gracious, this thing is aggravating, 3x plus c. Right? Now, let's raise both sides to the e. Okay? And this will just be a y plus 2. You could put the absolute values in here, but you see, this thing's always positive. Okay? So this will be y plus 2 is equal to e to the 3x times e to the c. Okay? Because you can do that with exponents, remember. 7 raised to the 4 plus 3 is 7 to the 4 plus times 7 cubed, right? It's just the principle of exponents. It's, yeah, right, okay. So same thing here, it's just e is the base and 3x plus c is the thing. So basically, this would just be some constant. So let's make this a c1 so we can make this c e to the 3x. And then subtract 2 from both sides. And there's your y is equal to this, y is equal to that. Same thing. Okay? Separation of variable is much easier if you can do it. These two you could. Don't worry. There's plenty you can't. Okay? So knowing the technique with something simple like this, then it'll be easier to do it when they are a little more complicated. All right. Now, and again, I should have put the interval minus infinity to infinity for x. Okay. Now, if you did do a graph of these, these function y is equal to c, and these are a variety of c's. Now, when c is equal to 0, you got y is equal to negative 2, which is, of course, what you get here. When c is equal to a positive number, I think those are when they're going up like this. A negative number would be going down like that. A little bit of a problem here because we remember we said these down here kind of are not allowed. So I think that's why they put them in a light shadow there, because this y plus 2, I guess they could be allowed, but that's your absolute value. So it's not really clear. I guess that takes care of it. They just, so it doesn't matter really so much about the y is what the c values are, and that would be determined by your situation. Okay, so now let's move to what they call the general solution at the bottom. Suppose again that the function p and f are continuous on some common interval I. In the steps leading to what we just did on the previous page, the last thing we did last time, that formula you came up with, which is really a big pain in the neck formula. Don't ever try to memorize the formula. But when you came up with that, we showed that if 2 has a solution on I, it must be of the form given in 4. Conversely, it is straightforward exercise, they say. Usually, when they say it is a straightforward exercise, it's anything but. In differentiation, to verify that any function of the form given by 4 is then a solution to the differential equation 2 on that interval I. In other words, 4 is a one-parameter family of equations 2, and every solution of 2 is defined with blah, blah, blah. Therefore, we call 4 the general solution of the differential equation, okay, on that interval I. This is so much blah, blah, blah. I don't think there's anything super critical in what they're saying. They're probably going to bring up a few cases you have to watch out for. Oh, and here they're just saying, what if you had an initial value? If you did, plug it in, find out what the C is. So let's do the general solution, example 3. All right. Let me untangle my pen again. It gets tangled so easily. Here we have solve x dy dx minus 4y is equal to x to the 6th e to the x. Okay? First question, is that a linear equation?
No.
Second?
No.
In y? Linear in y?
Yes.
Yes, okay. The x's don't have to be. It's linear in y because your y, dy dx is by itself here. It has a function of x there, that's okay. And it's by itself here, not squared, not cubed, not to the 1/2 or anything else. Not times the dy dx, you know, just a plain old y. Yeah, it has a coefficient. It could have been a coefficient function of x. That would have been fine. But it has no more y's. Only a dy here, only a y here, and only x is up here. Certainly not linear in x, but in y it is a linear function. Okay. Is it in standard form?
Yeah.
No.
No, because we got.
Yes, we want this naked.
Yes, we got to divide by x.
Yes, by what?
Divide by x.
Yes, okay. Divide everything on both sides by x. So that gets me down to x to the 5th on the right-hand side. Okay? Got it? So that goes to 1. Now we have it in standard form of a linear equation. Now, a little pause here to say, is this one also separable? Is this separable?
I'm going to say since the last one was, this one is.
The problem is you could add the 4y over x to both sides and get it over there, but then it's added to a function of x, and there's no way you could divide out just the y to get it by itself on this side and the x is on that side. This one I don't think is separable. Before it was, because it was a y on this side and a constant on that side. With x's on that side, you move that over, you have a function of x plus some function of x times y. Well, I can't get the y's by itself without having x's mixed in with it. So, no, don't think you can. So this one we can't go back and check at the end to see if it works by separation of variables, because it's not separable. So this one, this is the only way we could. Okay, so what's next? We got it in standard form. Next thing, we identify our P of x. And what is a P of x? Minus 4 over x. Perfect, okay? That is some function of x alone. And what do we do with that P of x? We integrate it. Okay? So the integral of that is, I'm going to bring the minus 4 outside the radical, and you have dx over x, integral of dx over x. And what's that? Second? Okay. Okay. We integrated both sides with respect to x. And I pulled out the minus 4 out of the integral over here and left me integral of dx over x. And what is that integral? Antiderivative of dx over x. 1 over x dx. Natural log of x. So it would be minus 4 times the natural log of x. And you could put that in absolute values if you want to do really picky about it. Okay, which we might. This one you don't ever put a plus c with. Don't. Okay, just leave it like that. Okay, what's the next thing we do? Yeah, make it the exponent of your e. Okay, now I'm going to use a property of logarithms, and that is a times the log of b is the same as log of b raised to the 8th power. Do you remember that? Okay. Yeah. It's the whole, or partly, part of the principle of how you can use a slide rule, okay? This is a characteristic of logarithms. See, a log takes a big number and makes it into a smaller number. You know, that's why you use logarithm. 4 million could be something about 6 point something. You know, it just makes it a much more usable number. That's what logs do for you. And so that's a principle of logarithm. So in our case here, it would be log of x to the minus 4. This thing right here, before we take the e for it yet, is log. You could put the absolute value x if you wanted to the minus 4. You just do that. Okay?
You don't have to have absolute values.
Yeah, you don't have to anymore, because if you wrote that 1 over x to the 4th, which would be a legal thing to do too, you don't need to, because that's always positive. You know, whether x is positive or negative, it's always going to be positive. But I'm going to leave it like that for now. It doesn't hurt anything. So this is e to that. Well, what is e to that? I write down my e here, but I could have left it in there. Okay. What is e to the log of something? Whatever the something is. That's x to the minus 4th. Okay. So there's our integrating factor. So what do we do with it? We multiply that by everything on both sides of our equation. So here we have x to the minus 4 dy dx minus okay, we got 4 over x, and we multiply it by minus 4. That'll be 4 over x to the 5th, right, times y, is equal to, and we're multiplying this by x to the minus 4th, and you had x to the 5th, so that just leaves you x e to the x. Now, was that a bit of too much of a shell game there? Were my hands going too fast?
Yeah, a little bit, yeah.
Okay. Our integrating factor is x to the minus 4. So it's x to the minus 4 times dy dx. That's times the first one. Okay. Now, x to the minus 4 is the same as 1 over x to the 4th, right?
Yeah.
Okay. So 1 over x to the 4th times the minus 4 over x, which is what that is, that gives you minus 4 over x to the 5th times y is equal to, and this is 1 over x to the 4th times x to the 5th. The x to the 4th down here marks out all but one of these x's, and then it times e to the x. Huh? Okay.
I'm definitely going to go back and rewatch this one.
Okay, well, okay. Multiplying by our integrating factor, you can write that as 1 over x to the 4th, right? So this could be 1 over x to the 4th dy dx plus, and then you multiply that one, this term right here, by 1 over x to the 4th, and that makes it minus 4 over x to the 5th times y, right?
That's what I'm losing. Say that again, or then.
Okay, this is our equation in standard form. dy dx minus 4 over x times y e to the x to the 5th e to the x. That's the equation.
Right.
We got our integrating factor is x to the minus 4. Let's call it 1 over x to the 4th. So 1 over x to the 4th times dy dx, or x to the minus 4th times that, whichever you want to call it. And 1 over x to the 4th times this would be minus 4 times x to the 5th. So that's 1 over x to the 4th times 1 over x. 1 over x to the 5th times y. And then 1 over x to the 4th times x to the 5th. Well, x to the 4th go to x to the 5th, x times. Okay? And then e to the x. So here's my new equation. Okay? Now, supposedly, this thing is a perfect derivative of a product of two functions. And supposedly that perfect thing is d by dx of x to the minus 4 times y. Okay? Supposedly that's it. Let's see if it is. It would be the first times the derivative of the second. Yeah, that's perfect. Right? Plus the second, y, times derivative of this one. Derivative of this one would be minus 4 x to the minus 5. Ha! It is. Okay. And that then is equal to x e to the x. Well, let's write this in differential form. Put in our dx over there. Integrate both sides. Okay? Integral of a perfect derivative is just what's inside. So you got x to the minus 4th times y is equal to, now, how are we going to do that integration? L2. Yes, sir. Oh, yeah. Okay, Mr. Stallworth, yeah. No, okay. Excuse me, just a minute. Let me pause this. Y'all be.
So it should be x squared e to the x over 2.
Okay.
Am I wrong?
That's at least part of it, but not quite. This is a product here, isn't it? Okay?
Oh.
And usually when there's a product, you kind of have to go back and undo a product rule, and that technique is called integration by parts. Remember that? Oh, yeah. Good stuff, Maynard.
No, I don't remember that at all.
You don't?
Nope.
Okay.
That's in bad days.
All right. Here's what you do with integration by parts. It always has to be a product. And you let one part be a function you're going to take a derivative of, and the other a function you're going to integrate. Okay? So it's sort of like a substitution, only you're substituting two things, a u and a v, usually. We love u's and v's. And so the first thing is site. Now, what you want to do, you want to pick the one that you're going to differentiate to make it simpler. And the one you're going to integrate, you hope it doesn't make it any worse. Okay? So if you differentiate x, that does get simpler. If you take the integral of e to the x, it doesn't get any worse. It's still e to the x. Okay? So that's what we're going to do. Let u equal x and dv equal e to the x dx. Every time you have a d, you have to have d on both sides of the equal. Okay? So what we're going to do on the next line is differentiate the first one, du equal dx, and integrate the next one. V is equal to e to the x, right? Now we don't do a plus c yet. We'll wait and do that at the end. So this is integration by parts. You split it into two pieces, differentiate one, integrate the other. Okay, now here's what your answer is then. Your answer is going to be the product of these two, the u and the v. So this thing is going to be x e to the x, it's a pretty ugly e, minus the integral, we still got an integral here, of the bottom line here, v du. But v du is pretty simple, e to the x dx. I can integrate that one. What is that? E to the x. So that's how you integrate this thing. X e to the x minus e to the x. Okay? Now if you don't believe it, then okay, this is it. I just didn't have much room. Okay? Take a derivative of this thing. Well, this is a product, so that would be first on the derivative of the second. So x e to the x plus 1 times, okay, derivative of this times that, e to the x, minus e to the x, e to the x minus e to the x, go away, you have this, that's exactly what you had from that. So yeah, it works. It did. Okay? So your y, when you integrated this side, x to the fourth minus 4 times y is equal to the integration of this side, which is x e to the x minus e to the x. And this one you do need your plus c at some point. Okay? So here's what we're going to do. We want to isolate the y. So we're going to multiply everything on both sides by x to the fourth. Right? No, 4. Or divide by x to the negative 4, which is multiplied by x to the fourth. Oh, okay. And that will make that a 1. Right? And this multiply x to the fourth will make that a fifth, and this will have a x to the fourth, and this will be an x to the fourth. Okay? So now we have y is equal to x to the fifth e to the x minus x to the fourth e to the x plus c times x to the fourth. One parameter system. Now, that's a little bit of an awkward looking answer. So let's see if we can clean it up a little bit. X to the fourth, factor that out. You have an x e to the x minus e to the x plus some constant c. Now I bet you that's not how they leave it, because they never leave it in the simplest form. Actually, they left it in exactly the form I had before. Okay, sorry. They had it in exactly this form here. They left it just like that. Y is equal to x to the fifth e to the x minus x to the fourth e to the x plus c x to the fourth. Wow. Okay. So forget about doing that. You could have tried to clean it up a little, make it easier to write, but they weren't at all interested in that. They left it just like that.
And so explain how that's the general solution.
Yeah. Okay. That is your general solution. Now, they need an interval. We did the integral, but they need an interval. Well, the interval goes back to the fact that, of course, your x can't be 0, right? And this whole thing about absolute value, it'll be better if we just keep them positive. So our interval is all x is greater than 0. That'll work for everything there. Okay. Negative x's work okay, except for the fact that this becomes negative at some point, you know, and those two remain positive, but who cares? Oh, and this whole term is negative, so these could easily outweigh that one and turn it all negative, and then you'd be log of a negative number, and we don't want that. So let's just leave x is greater than 0. And I think that's what they specify here. If I can find it. Yeah, 0 to infinity. So the interval is 0 to infinity. Not counting 0. Can't have 0 because that would have really messed us up in that very first step we did. Divide it. Well, but then too, if you think about this, x can't be 0 up here either because then you don't even have a differential equation. So no, you don't want your x being 0. Okay? You wind up with 0 minus 4y is equal to 0. And that means y is equal to 0. Big whoopee-doo. That is a very exciting seeming system. Okay. Now, except in the case in which the lead coefficient is 1, recasting the equation 1 into standard form requires a division a1 of x, you know, that whatever coefficient. In our case, it was just the x here. Values of x for which that's true are called singular points of the equation. They are potentially troublesome, just like we saw here, and the discontinuity may carry over into solutions of the differential equation. A lot of blah, 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 and not telling you a thing you can do about it. You know, you just have to be careful. In other words, x can't be 0. But of course, in the original equation, it would make sense for x to be 0.
So they're saying that because the x, or whatever is there,
yeah,
that's called a singular point.
Yeah. 0, 0, like I just said, if x is 0, y's got to be 0, so yeah. I guess that's technically a solution, but it's not a very interesting solution. And that's called a singularity, singular point. Okay. Not quite a singularity, a singular point. All right. How about example 4? Have we time?
4 minutes?
4 minutes?
No, not even 4 minutes.
Not even 4 minutes. I have a feeling I can't do example 4 in not even 4 minutes. So let me just give you homework exercises. And we'll pick up with example 4 next time. And let me wipe out my previous mark on this page so I won't be confused about which one it is. And I'll put this back in place. So we made decent progress today. You feel better about linear equations now?
No.
No, okay. All right, exercises 2.3. Any of the odds that you can find in the back of the book of 1 to 23. Okay? I think you can do some of, maybe not all of, the odds 25 to 35. Well, wait, we haven't done one with a... Okay, let's hold off on those. The first ones are the general solutions with a single constant. Okay, so we'll go from there. We'll pick up the others when we do that next example. All right, any questions?
I have
Yeah.
a couple questions about the test.
Okay. I can do them while we got it up.
You want to record?
It's what?
You want to record?
Yeah, we can. I mean, that way everybody gets to hear the same thing. All right, what we got?
I'll just through this extremely slowly, and I'm not sure why. I'm actually starting with number 4, verify that one parameter family is an implicit solution of the differential equation.
Right. Okay.
So how am I supposed? Maybe I'm missing something. How am I supposed to verify a one parameter family? And
Okay.
if I've worked this down, it is not. It is implicit, definitely, because I just can't seem to separate.
Okay. That's what I was just going to do, is go back and see if I could find one in your exercise set that was an implicit. Oh, I can't even find the exercise set now. Oh, I see. Did it go far enough back? 1.2.
Yeah. No, implicit is not a 1.2. Implicit is
1.1.
Yeah, 1.1 is 7 actually. Example 7 is the verification.
What number did you say?
Example 7.
Oh, example 7.
Oh, yeah.
Oh, okay, I'm sorry. I was looking at exercise 7. Okay. No, example 7 is fine. Yeah. Okay. Now, that's very similar to one we had. I was just going to see if...
Because the thing that aggravates me about this example is because they work it all the way down and then they say, yes, it's explicit.
Right.
Well, we're looking for implicit. Because this is
Oh.
verifying.
Yeah.
We're wanting to verify that it's a implicit one
Yeah.
parameter family.
Right. Well, okay. Let's take that, and just so you remember here. Okay. Here is, okay. They give it to you in reverse order from what they do in the book. Oh, no, they don't. It's the same thing. Here's the equation. X squared plus y squared is equal to 25.
Yeah.
Okay. Now, and it says verify that this dy dx is equal to minus x over y is a solution, and they say over the interval minus 5 to 5, okay, of that equation. Well, what you have to do is differentiate this equation, okay, and what would that be? 2x plus
2y.
More than that, dy dx, because y is a function of x. Chain rule, your favorite, is equal to 0. Now solve for dy dx. Well, first I would subtract 2x from both sides.
Yeah, subtract 2x, we got
2y dy dx is equal to minus 2x, right?
Yeah.
And then divide by 2y.
Yeah, it does.
Dy dx is equal to minus x over y. And that shows it.
Okay, well then all you've done is just...
Yeah, you differentiate
Yeah.
the top, and that's exactly what you do. You differentiate this one.
Yeah.
Remember that everywhere you see a y, when you differentiate it, you got to put a dy dx.
Okay, that's my major stumbling point. Why are we doing that for y? Because I would think that we would want to isolate y. I would think we would do
Okay.
2x dy dx. because we're trying to isolate 2y. Is that correct?
Okay. You're trying to isolate the dy dx. That's what you're asking for here. Well, actually, this one, you actually can leave a y on this side. You don't even have to isolate it. You have to show that when you take the derivative of the first thing, implicit differentiation, you get the second thing. Here, the second thing had dy dx by itself. In this problem, it's not by itself, but you can still do it. So basically, you differentiate this. But now the question I thought that you were saying, why do you need a dy dx? Well, y is a function of x. X is the independent variable. You see that here. Y is the dependent variable. So when you take the derivative of x squared, it's 2x, and if you wanted to, you could say dx dx. But that's 1. Right? And then when you do this one, 2y dy dx. But that's not 1. And that's what you're trying to isolate here.
All right.
And when you take the derivative of this, you get a 0.
That's where my big hang-up was right there.
Yeah. I thought it was probably the implicit differentiation part of it. And yeah, that's exactly right. Okay. And actually, this one, when you do it, you'll see one thing works out really nice. You got 2y terms. On both of those, you have to do a dy dx. But you only have one of them. And then you can factor that out, and you're left, I think, with what you see as a factor there. So I think the rest of it will be not as bad as you were afraid.
Okay. I haven't attempted number 5 yet, but I've looked at 6, 7, and 8.
Uh-huh.
And
oh, I'm so sorry. Those turn out to be
bears
and a half. So slug away. Try not to get lost in your slugging, and give it your best shot. You're definitely not going to be able to get the answer on that little line there. So you're going to need another piece of paper, something on the back. But
so we're doing the exact same thing.
Very similar to what you did in number 2, in fact. Only here you don't have any C's in there. Okay, it says verify that the indicated function is an explicit solution of the differential equation.
Right.
So here's your solution, an explicit solution. So you have to do, see, this one doesn't have a first derivative, but it has a second. You still have to take the first derivative of this, and that's the product rule and the log and all that involved. And that's the product rule too, and that's the product rule with the log in it. And actually it doesn't come out quite as bad as maybe you would think it would. But you get that, but then you have to take the second derivative, and then you go back and plug in that whatever you get from the second derivative plus the function itself, which is right there, see if that indeed equals secant that. Yeah, and if it does, you've shown it. So you can't possibly do that in one line. That's going to need the back piece of paper or
well, since it worked out better for the number 2 on a Word doc, I'm going to do that on Word doc too.
And then the second one is basically the same, only it is really a bit because you have logs and signs of logs and stuff, so you have to just keep up with and a log of a cosine of a log, product with a cosine of a log. But I did not realize they would give that messy a problem. I got this out of, a source for, it came with the book. And the answer is not that bad, but getting there is awful. Okay. But, slug through, do it on another piece of paper or Word document, whatever you want to do. And again, you take the first derivative, this time hang on to it, and take the second derivative, then plug it in and see if you get back to, when you take this function and its first derivative and its second derivative plugged in here, you get that thing right there. And it's just, it's a slugfest, is all it is.
Yeah, so 6, 7, and 8 function the exact same way.
Yeah, basically.
Because that squaring of the dy dx throws me off, but I guess.
Okay. Well, again, here's the function here. Yeah. Okay, after that semicolon, there's the thing. Verify that expression is an explicit solution. So take this and take a derivative of both sides. This is more like number 4. I think, no. One we were just talking about, explicit solution.
Yeah, number 4.
Was it 4? Okay. Yeah, number 4. Because that one you can't do it explicitly or not easily. So do it implicitly, just like we did 4. Take the first derivative, get that, and that can be explicit, and then take the second derivative of that. No, you don't need a second derivative. That first derivative, then once you get that first derivative, square it. Because that's what the dy dx squared is.
Okay.
Plus 1 is 1 over this thing.
Verify that it's...
Okay.
Yeah.
Now, it's 1 over y squared. But notice here, this isn't very easy to solve for y, but you can solve it for y squared explicitly. Right? And so whatever that is for y squared, put 1 over it and see if it's equal to the other side. That one's really not quite as bad as you might guess. And then I think number 9 is rather straightforward. They give you 2 initial conditions, and
I haven't even attempted.
Oh, okay, yeah, okay. Yeah. Okay.
So if this is solving for explicit or implicitly,
Right.
because we're doing dy dx of 2y, how would we do it explicitly?
You can't, that one's not, if you try to do it explicitly, what you have to do is y squared is equal to 25 minus x squared. You know, subtract x squared from both sides. Then you solve for y, taking a square root. So you have y is equal to plus or minus the square root of 25 minus x squared. Well, you got 2 solutions there. And then you have to do one, then you have to do the other, and take the derivatives, and it really is a bear. Okay, so doing it implicitly is just that. You know, it's done. You don't have to split it into 2 different functions and then show that both of them work and that kind of stuff. This just shows it right there.
That's good. That makes me feel better.
Yeah.
Because this example that they have here for implicit solutions, it works all the way out to, for whatever reason, they work it out explicitly.
Well,
maybe I'm wrong.
Well, at the very end, I mean, the dy dx is an explicit solution, but, the one in the book, is that what you're saying?
Yeah. Page 8, number 7, example 7.
Yeah, but they do it implicitly. That exactly,
right there.
Their 9 is exactly what we did there, implicit. And then basically what they're saying is that does it for this whole function here. It's not even a function, okay? But that gives you for the whole thing, the differential equation there. If you did it explicitly, you either do the top half or the bottom half. That's positive square root of 25 minus x squared, and this is minus the square root of 25 minus x squared. And you have to do each of those separately and then put them together, and it's just a big pain in the neck. And this one's only good for, and they're all only good for x from minus 5 to 5. You could include the minus 5 and 5. There's nothing that says you can't, because that would work, but they, for some reason, just do it less than, and they put parentheses here. I think at some point I figured out why they may have done that, but, oh, no, I can't. Oh, that's why. No. I was going to say at -5. I can't think of any logical reason they didn't. I'm sure there must be one. They didn't include the 5, but it really doesn't matter. It's just 1 point.
Yeah, good. That makes me feel a lot better.
Yeah.
making it much more difficult than what
Yeah.
it actually is.
No, that's my job. Okay, you just do what I think. Okay.
You sent out a key from these people, Larson.
Uh-huh. No, this is something else. Zill. Cengage or what?
That's it,
Yeah.
Cengage. I tried to go to Cengage and
Oh, the class key?
yeah, I tried to enter that, but I could never figure out where it was supposed to go. So I
Okay.
guess I need to keep poking.
Did you do Cengage Unlimited? Well, then you don't need it. That was, you bought the book.
I bought this on Amazon.
Oh, yeah, fine. So you don't need this.
Okay.
Because you don't have a receipt that has a code for the thing. Okay. Yeah, you don't need it. It's only for the people who did choose to go to Cengage and not buy the book to have access to the ebook, you needed the code. But since you got your book by Amazon, you don't need it. Yeah. But I needed to provide it for the people who did go through the Cengage.
And Mohammed has,
Yeah.
he's got it on.
Yeah.
So I've done research for your professor, 1971 at Georgia Tech. I can't find his name for nothing. Do you remember his name for your
Yeah.
individuals?
Yeah, but I mean, it wasn't his. Just everybody used the same book then. His name was Ray, Dr. Ray. I don't remember his first name. Can't remember if it was R-A-Y or W-R-A-Y. I think it was W-R-A-Y. You could try both spellings, but it wasn't just him. It was the book used by everybody for differential equations. It's Math 207. No, 209. 209.
209?
Yeah.
Jeez.
Yeah.
Okay.
Ours is 238, but theirs is 209.
Because I found some books that were published like in 68, 67. I found one that was published in 71, but I was thinking you probably weren't using that one.
No,
That would have been too early.
I would think so, because I think I even had a used book. So
Yeah.
yeah.
Okay. Anyways, I've got a couple images of some books. If I printed them off, would you recognize it?
I might, yeah. You see, I was in Navy ROTC, and they paid tuition fees and books, so they issued me the book if they had it, and then at the end I had to give it back to them. Now, my calculus book, I had it for 5 quarters, so they said, you can keep that one, because it was pretty worn by the time I finished it. And they said, you can keep that one. But the differential equations, it was a book not much different in size from this one, but it was just so straightforward. You just did it. You didn't have all the...
I don't like this one.
Yeah.
I don't like this one.
The only reason I got it is it's the one that the other schools seem to be using, and that some of the 4-year schools seem to, at least the one who told me said that's what UA uses. So.
Okay.
But I've been through several before this one, and this was the best of those. I mean, some of them are that thick, and they get into partial differential equations and all sorts of esoteric stuff, that this is better, but still leaves a lot to be desired.
Yeah. All right, well, I'm going to go home and work on these then.